Okay, this video will just go over the equations that you need for chapter 43, which is on nuclear physics. The first equation on that formula sheet is R equals R0 to the 1/3. This is the formula for calculating the radius of a nucleus. So if you have a nucleus, remember inside here are the neutrons and protons, and the radius of that nucleus is R. A is equal to the number of neutrons plus the number of protons. So Z is the proton number, and N is the neutron number. Collectively, neutrons and protons are sometimes called nucleons. Okay. The next formula on the formula sheet has to do with binding energy, EB, Z, MH plus N, M, N minus AZMC squared. Okay, so what all this has to do with, if you take a nucleus, like let's say we take lithium, and inside of lithium, one of the isotopes is 3 neutrons and 3 protons. That's the nucleus. The electrons are outside of that. In this case, there'd be 3 electrons in that neutral atom. Now, if I'm able to split up that nucleus so that I had all these neutrons and protons sitting by themselves over here, proton, 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 neutron, neutron, neutron. If I add up the mass, and then you got to deal with the electrons. So there's a little bit of energy associated with the binding between the nucleus and the electrons. So usually what we do is we sort of take the electron, make it a little unit with the proton, and that's hydrogen. That's the mass of a hydrogen. So that little unit, that's what this is, that mass. And Z is the number of these little units that we have. So it's the same as the number of the protons. So in this case, Z would be 3 because we have 3 protons, each of which has a little electron attached. This Mn is the mass of the neutron, and N is the number of neutrons. So clearly the mass of these would be Mn times 3. Now, if I add all this up, that's what this first 2 terms are. I get a certain mass. Let's just use some goofy numbers, 10 kilograms. And the crazy thing is that if I then join them all together into the lithium atom, the full atom, that's this. So this would be the mass of the whole atom. And that would be given in tables. So this is it when it's all together. It turns out that the mass of these individual things is bigger than the mass when it's all together. And the difference in that mass, those masses, is called the binding energy. The C squared is to convert kilograms into joules. So remember, E equals mc squared. So the units here, this would be joules. This would be kilograms. And that's the speed of light squared. So that's 3 times 10 to the 8 meters per second squared. Okay, so that's what binding energy has to do with. Now, this is an enormous amount of energy per nucleon. Often what we do is we calculate the binding energy per nucleon. So we go per A. And for the bigger nuclei, like uranium, thorium, radium, those kind of things, this is a huge amount of energy. And this is the amount of energy that gets released when nuclear reactions take place. So when nuclei change. Now, nuclear reactions don't just go around taking place any old time. It's much more difficult to have a nuclear reaction. Either it's natural because the nucleus decays, or you have to bombard the nucleus with something to get it to do that. Okay, so that's what that formula is about. The next formula has to do with radioactive decay. So N of T is N0e to the minus lambda T. Okay, so this has to do with radioactivity. So some nuclei are unstable, and in order to become more stable, they will decay, they'll break up. So like carbon-14 will break up and to become more stable because it's unstable. Uranium, thorium, all those big radioactive isotopes will decay. So n is the number of undecayed nuclei. So it's the number left after a decay has happened. And 0 is the original number. Now, sometimes if you're given a mass, you're going to have to know the mass, the atomic mass number. Those tables are all in the textbook on the internet. You can find those numbers. So this is the original number of nuclei. Obviously, each atom has one nucleus. Lambda is called the decay constant. Oops. And that has to do with the probability that any given nucleus will decay in any given unit of time. So the units for lambda would be in 1 over the time, whatever the time unit is. So it might be 1 over days, 1 over seconds, 1 over years, 1 over millions of years. Decay constants can wildly range from tiny numbers to enormous numbers. And then t is time. And don't forget that you have to have no units up here in the exponent. So whatever time is in, if it's in days, lambda has to be in 1 over days. If it's in t's and seconds, this has to be 1 over seconds. Okay, and this is radioactive decay. So this is this curve that goes like this, exponential decay. That's n as a function of t. Okay, and that negative is what makes this go down. Now associated with that is a half-life. So what the half-life means is you start with n0. In a time of 1/2, you're down to half of n0. And this time would be t 1/2. And then it keeps going. Another, cut that by half, and you're over to 2 half-lives. Cut that by half, and so on, off to, well, it never gets to 0, but getting close to 0 here. Okay, so the formula that relates those is, the one on your formula sheet is 1 over lambda is the half-life over the ln of 2. Paying the ln of 2 is 0.693, but you're just going to put the ln of 2 into your calculator for this. They also define something, this is not a very common thing to define, but it's called t-mean. And this is sometimes called the lifetime. It's the average time that any given nucleus will last before it decays. Okay, so this lifetime, this is average time a nucleus waits to decay. Now, nuclear decay is a completely statistical problem. You cannot take any one nucleus and say, okay, it's going to decay in 10 minutes. All you can say is that if the half-life is 5 years, then, and if you start with 100 nuclei, well, in 5 years, half of them will have decayed. And you can't say which ones, and you don't know when. So it might be the first second, boom, 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 a whole bunch decay. And then they wait, and then boom, and then maybe another one. And so you don't know which ones do it, and you don't know when they do it. You can simply statistically say half of them are going to decay within that half-life. Okay, now another quantity that's not on your formula sheet, but that you do need to understand is called activity. And this has to do with how radioactive a sample is. The higher the activity, the more particles it's spitting out every second. And so, unfortunately, it gets the symbol R in most textbooks, but it's not the R, the very first equation that had to do with the radius of a nucleus. This is R is called activity. And the units for this are decays per second. Now, curies are also a unit of decays per second, as are becquerels. And so the curie and the becquerel are also used for the values of activities. The relationship between activity and n is that R is equal to lambda n. It's also equal to negative dn dt. So it's the rate. It's called the rate of decay. That's what activity is. It's how many per second. Now, if you actually do this, like take the derivative of n, go dn dt, and you would get d by dt of n0 e to the minus lambda t Not sure how that line just got there. N0 is a constant. Bring down the negative lambda, and then leave e to the minus lambda t is equal to minus lambda n0 e to the minus lambda t, which is equal to minus lambda n. Okay, so now that's why there's a negative up here in this formula. So R is lambda n is negative lambda n, which is the same, lambda n. Okay, so and if you need the activity at time 0, R0 is just lambda n0. Okay, so sometimes that's a really handy formula. Remember, this is the number of nuclei, and this is the rate of decay. And this is the decay constant. That's the per time that you need. Okay, so that should do it for this.